Welcome, Mr. Perry here. We're going to be taking a look at part 2 of Forces and the Universe. We're going to be covering gravity, electrical, magnetic, and wave energy forces. So read along with me. Let's begin. Kinetic energy as waves of energy in motion. Some energy waves can be reflected or bounce off certain objects like sunlight or roads. Some can be absorbed or taken in by certain substances like the earth and living things such as plants and animals. And some can be refracted or bent like in water. Mechanical waves or energy waves like sound or seismic or earthquake waves. They must have particles like air, solids, or liquids to go from point A to point B. They cannot travel in a vacuum or in space. They can be both longitudinal and transverse waves, which we're going to find out a little bit more about. Electromagnetic waves are waves in the electromagnetic spectrum, like radar, microwave, light, radio, etc., that can travel without particles like in a vacuum and through space. Some can travel along particles, but they are not actually a part of the substance. They only travel along transverse waves. Let's learn more.
How do waves behave? Badly? In this video, we're going to look at how light and sound waves behave. Before we start, you should know that waves can be transverse or longitudinal. To learn more about the properties of waves, watch this video first. Transmission, reflection, refraction, diffraction, absorption, and scattering are all typical wave behaviors. Reflection is when waves bounce off an object. Sound waves are reflected by hard, flat surfaces and is why we get echoes. You hear a delay between the original sound and the echo, because the echoed sound waves have to travel twice as far to reach your ears. Smooth surfaces like glass or polished metal reflect light in a regular way, so a reflection can be seen, like a mirror, or seeing your face in a calm pond. Transmission is when waves keep traveling in the same direction through an object, like light through a window. Absorption and reflection often go hand in hand for light waves. White light contains each wavelength, so all the colors of visible light. The color of an object depends on which wavelengths of light it absorbs and which it reflects. White objects reflect all the light that hits them and absorbs none. Black objects reflect none and instead absorb all the light that hits them. A red object absorbs all the wavelengths except the red, which is reflected. And a green object absorbs all the wavelengths except the green, which is reflected. Are the new people upstairs really noisy? If they carpet their floors, add curtains and furniture to the room, then you'll notice that they'll become much quieter. This is because some objects absorb sound waves. When sound and light waves pass across a boundary between two substances, like air and glass, they change speed. This is because the substances have different densities. The change in speed causes the waves to change direction, which is known as refraction. Because of refraction, things in water look closer than they really are. Water appears shallower than it really is. And a straw in a glass of water looks like it bends at the surface. Because the refracted light wavelengths make you think the straw is in a different place to where it actually is. When waves meet a gap in a barrier, they pass through the gap. They then spread back out after they pass through the gap. This is diffraction. The way the waves respread depends upon how big the gap is compared to the incoming wavelengths. We have diffraction to thank for loudspeakers. Sometimes waves depart from the expected path and spread out in multiple directions. This is known as scattering. We have scattering to thank for making the sky appear to be blue. The white light coming from the sun hits the molecules in our atmosphere, which causes the shorter blue wavelengths to scatter out in all directions. So waves behave in a variety of ways, depending upon what material they hit.
Energy as waves. Longitudinal compression waves. Energy carried through compressions or squeezing together, and rarefactions, which is stretching out of a substance like air or water. The slinky in the diagram moves back and forth, carrying its energy through compressions, which is squeezing, and rarefactions, which is stretching. Energy as waves, well, we have transverse waves. Substances moving up and down in S-shaped waves carry energy forward at right angles or transverse to the direction of the S-shaped movement. The slinky is moving up and down in an S shape, but the energy is traveling forward at right angles to the S-shaped waves. Think of shaking a blanket and how the waves move at a right angle. Measuring waves, well, we look at the peak or crest. That is the top of a wave. Our diagram shows that, where you see the peaks. And we have the troughs, which are at the bottom or valley of a wave. The amplitude is the height of a peak or trough. The greater the amplitude, the greater the energy. And the unit of measurement is meters. The wavelength is the distance between any two peaks or troughs. Closer the wavelengths, the faster the energy travels. The unit of measurement is also meters. Measuring waves, the frequency is the number of waves that pass by in 1 second. The unit of measurement is hertz. 1 hertz is equal to 1 wave passing by each second. Ocean waves are transverse waves that carry huge amounts of energy across the surface of the sea as they move up and down. Now, a wave of 3 meters, which is about 10 feet high, carries enough energy to power around 1,000 light bulbs in every 1 meter, which is about 3 feet of its length. Energy as waves, sound, and sound wave characteristics. Now, sound comes from a vibrating object. Your vocal cords, guitar strings are just a few, and they travel in longitudinal and transverse waves and can be carried by air, water, metal, and other particles, but travel fastest in solids. Sound cannot travel in a vacuum, that is, space where there is no matter, and the greater the wave's amplitude, the louder the sound, and the smaller the amplitude, the softer the sound. The farther apart the wavelengths, the lower the sound, and the closer the wavelengths, the higher pitch of the sound. Here's more.
Sound is basically vibrations, and we can represent sound using special diagrams that are kind of shaped like a mountain and a valley. And because these diagrams are shaped a little bit like mountains and valleys, we describe them as waves. Waves. I don't get it. We've all got a basic understanding of what sound is because we hear things every day. And we've probably got some idea of how we might describe some of those sounds. For example, we know that there are sounds that are high-pitched. And by contrast, there are sounds that are low-pitched. But what exactly is sound, and what is it about it that allows for this high and low pitch? Well, to understand sound, a good place to start is how loudspeakers work. Basically, when a loudspeaker is going to generate sound, what it has to do is move up slightly and then back down. And it's going to do this really, really fast in a little pulse. Now, as the loudspeaker does this, the air molecules that are immediately in front of the loudspeaker will be forced outwards. And those air molecules are going to collide with the next set of air molecules that are right in front of them. And then those air molecules are going to collide with the next ones in front of them, eventually transferring this little pulse away from the speaker. Now, this alone is not enough to create sound. In order for sound to be generated, this pulse has to happen repeatedly. It has to happen many times each second. The vibration of air molecules allows sound to travel at a speed of 340 meters per second. Now that sounds quite fast, but if we compare it to water, which is much more dense, meaning the molecules are much more close together, it is capable of transferring sound at a faster speed of around about 1500 meters per second. Now let's look at this diagram of air molecules vibrating as a consequence of this pulsing of a speaker. What we've presented here is something called a longitudinal wave, but it's a little bit more convenient to present sound diagrammatically using something called a transverse wave. On this diagram, we can see from the transverse waves that there are 3 waves within a time frame of 1 second. This means that the speaker is vibrating at a rate of 3 pulses per second. And this is telling us the frequency. Frequency has the unit hertz, and so we can say that this speaker is generating a sound of 3 hertz. Now let's have a listen to what 3 hertz sounds like. Can you hear it? No, and there's a reason for that. Human hearing is only capable of responding to frequencies in the range of 20 Hz up to 20,000 Hz. Anything lower than 20 Hz is described as subsonic, and our ears can't hear it. Anything higher than 20,000 Hz is described as supersonic, and we can't hear it. Let's look at a speaker in action playing a frequency of 30 Hz. Now on this speaker I've put a few little bits of polystyrene which are there to demonstrate the up and downwards movements of the speakers a little bit more closely. As we turn it on, we can see the little bits of polystyrene bouncing around all over the place. And if we play this back in slow motion, we can see quite clearly the upwards and downwards movement of the speaker. Now if we want to demonstrate this graphically, a device which takes a sound and represents it as a wave is known as an oscilloscope. If we look at this frequency being played through the oscilloscope, we can see our transverse wave. Now let's see what happens if we increase the frequency to 50 Hz. We can see that the bits of polystyrene are bouncing around faster and the shape of the wave has changed. Now let's look at it at 100 Hz. Notice that as we increase the frequency, we are increasing the pitch. As you can see, the transverse wave shape is changing, but what exactly do these shape changes mean? Well, the first thing to notice about a transverse wave is how wide it is, and this is referred to as the wavelength. If we have a longer wavelength, this means that we have fewer pulses in any unit of time, which means we have a lower frequency and therefore a lower pitch. By contrast, of course, if we've got a shorter wavelength, it means that we've got more pulses in any unit of time, therefore a higher frequency and a higher pitched sound. Another important thing to notice about transverse waves is their height. The height of the wave is telling us the amplitude. And when we're talking about sound waves, a greater amplitude basically means a louder sound. So by contrast, if we've got a less tall wave, then we have a softer sound.
So there you have it, Forces and the Universe, Part 2. This is Segment 1, which covers slides 1 through 8. And you have some worksheets to do. So, may the Force be with you. Let's get it done.